Hello, and welcome to Part 7 of the module providing a case study of Gang of Four patterns. In the previous parts of this module, we've discussed some of the patterns for our expression tree processing application. We first started by talking about patterns for tree structure and access, things like composite and bridge. We then talked about patterns for creating expression trees from user input. We talked about interpreter, and we talked about builder to create the composite, which gets joined with the bridge. And now we're going to talk about several patterns that help us to traverse trees in various ways. The particular purpose of these patterns are to traverse the expression tree and perform various designated operations. And you'll see what we mean when we talk about that a little bit later. The patterns we're going to talk about will first be iterator. We'll then talk about prototype as a way to help iterator do certain things more effectively. And then we're going to go ahead and talk about visitor. And these patterns all get combined together to form a pattern sequence that you see very frequently in certain environments. These patterns we're going to apply help us to decouple the expression tree structure from the operations performed on that structure, and to do it in a way that makes it easy to add new operations without breaking existing software. So let's talk a bit about the goals of this particular set of things. What we're trying to do naturally is provide extensible expression tree operations. We'd like to be able to create a framework to perform operations that will affect the nodes in a tree. For example, one kind of operation we might want to have is a way to print out all the nodes in the tree, some kind of pretty printer or some way of being able to let you see what the tree is. Perhaps traversed in different ways. We want to be able to traverse in pre-order or post-order, in order, level order, and so on. Another set of things we might want to be able to do, another type of operation, is to be able to evaluate the tree to get its yield or its result, its value. So for example, the tree we see here would give the value of minus 35. That's the yield of the tree. Some of the constraints and forces here, we want to be able to add different operations on the tree without having to do any surgery or modifications to the existing tree structure or the classes that are providing as part of that structure. And this is a little tricky if you think about it. Perhaps the intuitive or naive way of doing this would be to add methods on every node in the tree. Go back to our component node, for example, and we'd add a method like print yourself or evaluate yourself and so on. But we want to resist the urge to do this, because the minute you start hard coding or hard wiring the operations with the nodes, you've ended up making it difficult to add new operations without doing surgery on the tree classes and the tree composite structure and so on. So we're going to avoid doing that. How are we going to do this? Well, you'll see that there's several parts to our solution. The first thing we're going to do is we're going to encapsulate traversal. And to do this, we're going to apply something called an iterator. And an iterator will allow us to be able to traverse the expression tree in different orders, different formats, without exposing the representation details to the application. So here, for example, you can see that we have an expression tree, and we might want to be able to traverse this tree in different traversal orders. But we'd like to be able to do it in such a way that you can't tell by looking at the code how the tree is represented. And perhaps you might even want to abstract away what traversal order is being done when you write the code. And then, of course, you can configure how it works by setting certain options or properties that the interpreter can use to guide its actions. So we'll come back and see how we implement this in just a second. Here's the structure that we're going to use to do this. We're going to end up having something called the expression tree iterator impl hierarchy, where we're going to have in order expression tree iterator impl, level order expression tree iterator impl, pre-order, post-order, and so on. And those things are combined together in a traditional inheritance hierarchy. And then as you see here, we're going to apply our good friend, the bridge pattern, in order to be able to make this all work together in a way that will be usable within C++ for value-based STL-like syntax and semantics. Now, we don't have to do this. If we were programming in Java, we might leave that part out. But when we use C++ and STL, by using the bridge pattern, it greatly simplifies the memory management, and it also encapsulates variability quite effectively. Here is the interface portion, or the abstraction portion of the bridge pattern. It's called the ET, or expression tree iterator class interface. And what you can see here are some interesting things. First of all, this plays the role of the abstraction or the interface in the bridge pattern. So this is what will be used by our various STL algorithms. And it also defines all the various operations that you've come to expect from iterators in STL. So things like plus plus, both pre-order and post-order plus plus. It defines equality and inequality of iterators. It defines the operator subscript or operator star for being able to dereference the iterator, and so on and so forth. So from a commonality and variability point of view, we now have a common interface that will be used in a way that conforms to what's expected by STL, but we'll be able to vary the particular type of traversal that's being done by using the next class we'll look at on the following slide. This particular class is called the expression tree, or ET iterator impl, and it's the root class or the base class of a hierarchy of different traversal algorithms. And we're going to be able to use this class to provide a common interface that can then be systematically varied in order to traverse the tree in the different orders that we want to be able to support. If you take a look at this particular implementation, I've kept it looking pretty similar to the way that the interface class works for bridge. It has the same C++ STL-like operator overloading. We have operator equality and inequality, operator plus plus, we have operator star for dereferencing, and so on. That's actually not required. I could have some different interface here if I wanted to, perhaps one that was even a little bit easier to understand. And because we're using the bridge pattern, the interface that's used by STL and STL algorithms and containers can be separated from the particular details of the interface that's used to implement that abstraction. The clone method we see here we'll talk about a little bit later when we talk about the prototype pattern, so keep that in mind. From a commonality and variability point of view, pretty much the same thing we saw on the previous slide. We have a fixed interface that's used to express the way we iterate, and then we can subclass to have different variabilities handled in a common way. The way that we're arranging these particular sets of classes is something that's defined quite nicely in the Gang of Four book as the iterator pattern, which is an object behavioral pattern. And the intent of this pattern is to be able to access all the elements in an aggregate without exposing the representation to the users. And you typically would use this pattern under several circumstances, one of which is you need to have different ways of traversing some kind of aggregate. For example, in our case, we're going to be able to traverse things in order, post-order, pre-order, and so on. You want to be able to have a uniform traversal interface over different aggregates. For example, think about the way that C++ STL works. We have different aggregates. We have different containers. We have vectors and decks and maps and sets and so on. But we use the same iterator interface to access those things. And then the other time when you would apply this pattern is when we have a need to be able to have the aggregate classes and the traversal algorithms vary independently. We might want to be able to support things that can be different, but we don't want to have those dependencies expressed in the particular relationships between these different parts of the code. Here's a diagram that illustrates how this pattern works. So we have an aggregate, which is something like our expression tree, and that has some kind of factory method to create an iterator. In this particular case, we're creating an iterator that may be the root of a base class hierarchy. It's the base class in a rooted hierarchy of nodes, like ET iterator impl. And then we can subclass to define various kinds of iterator implementations. So we might have pre-order iterator impls, post-order iterator impls, and so on and so forth. Now, it's important at this point to take a step back and look carefully at this pattern structure and ask ourselves, this is the only way we would implement iterators? And as always, it turns out the answer is it depends. Keep in mind that the way in which the structure diagrams are portrayed in any description of patterns is really just there as a heuristic. It's there as a guideline to help you think more visually and more systematically about the roles and relationships in the pattern. It is not a Procrustean bed or some kind of canonical form you can never deviate from. And this gives us a good example in which to talk about that. For example, if you compare the way that C++ iterators work relative to the Gang of Four Iterator pattern, you'll see some interesting differences. In particular, STL iterators have so-called value semantics. So as we see in this particular example, when you go ahead and call the begin method on the expression tree object, it gives you back an iterator. And that iterator is used by value. And it has operations like plus plus or dereference or not equals and so on. And those work on value objects. In our case, they work on expression trees. And so as a result, the memory management issues are basically hidden. You don't have to worry about any kind of deallocation because those things are covered by the way in which value semantics work in C++. And of course, in the way we use the bridge pattern in combination with composite to hide those things through reference counting. In contrast, the Gang of Four way of doing things has a bit more dynamic allocation taking place. So in their model, you go ahead and you create an iterator or pointer, and you call a factory method to get a pointer to the iterator. You advance through that iterator one at a time, and when you're done, since it was allocated dynamically, the iterator has to be deleted. Now, of course, you could always use some kind of auto pointer or unique pointer to do that freeing for you, but the point is it's a little bit different from the way that C++ works. As a general rule of thumb, the STL-style iterators are harder to implement because there's more pieces to think about and some subtle semantics to worry about, but they're a lot easier to use, and they work quite nicely with all the various generic algorithms in STL. Conversely, the Gang of Four way of doing things is a little bit easier to implement. There's less subtleties to be concerned with, but it's also somewhat harder to use correctly because you have to remember to delete the memory when you're done. The bridge pattern, of course, is what enables us to be able to use the expression trees in a common way with the value-based STL algorithms. Let's take a look at how we might do the same kind of thing in Java. Java iterators that are defined out of the box are much closer to Gang of Four iterators than the STL equivalents are. And that's because things are allocated dynamically in Java. But the good news is, because of garbage collection, you have much less work to try to keep track of. So it can do some of the work on your behalf. I also show an example on this slide kind of illustrating how a Gang of Four style iterator might look in Java. That's not quite the way that Java iterators are defined to work, but it's along the same sort of lines. Of course, it turns out that one of the simplest ways to use an iterator in C++ and Java is simply to use a for loop. So here's an example. What we can do here is we can use a range-based for loop in C++, which kind of bakes in support for iterators. And that's very simple. There's very little typing to do. Likewise, you can also do something similar with Java for each loops, which again are very simple. So this is a nice illustration of how patterns often find themselves institutionalized in programming languages, thereby making it much easier to program the patterns over time because it's built in to the language. Here's a very simple example of an iterator implemented in C++. This is using our iterator expression tree example. Here I show a portion of the implementation of the pre-order expression tree iterator impl class, which inherits from the expression tree iterator impl base class. And as you can see here, when the constructor is called, it pushes the expression tree onto a stack. Whenever you call operator star, which is the dereference operator, it returns the top of the stack. And whenever plus plus is called, it goes ahead and advances the next items in the expression tree by pushing things into the stack depending on what their values are. So it turns out that this particular way of implementing pre-order traversal is effectively using an explicit STL stack with all of its wonderful value-based semantics in order to be able to simulate recursion. We don't want to actually do this recursively because we want to get access to each element one at a time. And if we use recursion, we do the whole thing in one fell swoop. So that this is a nice example of how we can combine STL as well as patterns in order to be able to simplify the way that we write the iterators. The consequences of using iterator, very flexible. You can have the iterator and the aggregate vary in different ways. They're independent of each other largely. You can have multiple iterators traversing over the same aggregate, and they can keep track of their own progress and their own state individually. We also have some downsides, of course. There may be some communication overhead between the iterator and the aggregate. And this communication overhead can be particularly problematic when we start working with concurrent and distributed systems, as we'll talk about in just a second. Some implementation considerations to think about. Do you have the iterators be external to the aggregate, as we do in STL, or do you put them together? The downside with putting them together and making them internal is there's typically only support for one iterator at a time over an aggregate. How much work do you do to try to keep the aggregate structure encapsulated from the iterator? Do you make them friends? Do they know a lot about each other's private parts? Are they accessed only through well-defined setter and getter methods and so on? Kind of a trade-off there. There's also something called robust iterators, which allows the iterators to continue to work even if the underlying aggregate is modified, say its nodes are deleted or some nodes are added. Those are much more expensive and complex to implement, but they can be useful in some circumstances. There's also some other considerations if you start trying to apply the iterator pattern in the context of synchronization or multi-threading or distributed computing. Synchronizing iterators is a little tricky. You want to make sure you don't have so much synchronization that it's really slow, but you don't want to have too little synchronization and not be able to protect access to the elements in the aggregate or the iterators as they're being accessed concurrently. There's some other issues when you start spanning across address spaces or protection modes in an operating system where you may end up actually wanting to be able to batch together a group of elements and use something called a batch iterator, which is another variant and another pattern, in fact. Iterators are very widely used. They are heavily used in C++ standard template library. They're available in Java. They've been used in lots of various toolkits and ways of being able to access things in an object-oriented environment. And as I mentioned before, they're increasingly being connected together and implemented in the form of programming language features like range-based for loops in C++ or for each loops in Java. So part B of our solution, I mentioned before that there's multiple parts to what we're trying to do here. So part A was to be able to use the iterator pattern to get access to each element in an expression tree. Part B is to make it possible to define the actions at each step of the traversal in such a way that we don't end up hard coding the actions into the nodes of the tree, which would unnecessarily complicate our design. So what we're going to do here is we're going to have our iterator walk through the tree nodes one at a time. And for each node we get back, we're going to call a method called accept on that node. And if you recall, the expression tree bridge interface class had an accept method that then delegated or forwarded to the appropriate node in the implementer hierarchy. And when accept is called, what it does is it turns around and calls to something called the visit method on the visitor that was supplied to accept. This interaction is called double dispatching, and we'll talk more about that in just a second. So what happens here is when we called the original accept method, we passed in a visitor, and then when the visitor is called, when the visitor is passed in to the accept method, it turns around and it calls visit on the particular type of node in the composite. Now, this is a very complicated set of interactions, and we're going to walk through this one step at a time. But I wanted to give you the high-level overview first to see where we're headed. Notice, by the way, and we'll come back and look at this in more detail, we have something called static polymorphism that's used here when we visit the visitor and pass in the node to the particular composite. In this particular case, what we're going to do is we're going to take a look at the type of composite node we are. Are we a leaf node? Are we an add node? Are we a subtract node? And so on. And we're going to go ahead and call the appropriate visit method, which is actually overloaded using C++ function or operator overloading. So let's first talk about the visitor class interface. This is the interface for visitors that define all the operations that are performed for each type of node in the expression tree. If you take a look, you can see that we have a number of methods, all of which are called visit, all of which are overloaded by the different kinds of nodes we have in our composite. So we have leaf nodes, composite add nodes, composite subtract nodes, composite negate nodes, and so on and so forth. And for every different kind of node we have in our composite hierarchy, we're going to have a corresponding visit method in our visitor class. Now, from a commonality and variability point of view, the commonality is that we have all these visit methods, and we also have one method called accept, which takes a visit, a reference or a pointer to a visitor instance. From a variability point of view, we can subclass from that visitor interface to define the various kinds of actions we want performed on each of the different types of nodes in our composite. So we might have a print visitor, we might have an evaluation visitor, and so on and so forth. So it's these dual hierarchies working together that help to provide the particular solution we're looking for here. Now, the way of arranging these different roles and responsibilities is something called the visitor pattern, which is a Gang of Four object behavioral pattern. And in most people's opinion, the visitor pattern is the most complicated one in the Gang of Four books. So don't be dismayed if the first time you watch this video or think about these concepts, it's a little bit hard to follow. There's a lot of moving parts, and they have various intricate and subtle dependencies on each other. But you can go back and watch the video multiple times and take a look at the various books and literature and code and so on to get a better feel for how it all works. The intent of the visitor pattern is to centralize operations on an object structure, such as our composites for our expression tree, so they can vary independently but still behave polymorphically. That's kind of a mouthful, and we'll break it down and look at it in just a second. You might want to apply this pattern when classes define many unrelated operations, so printing, evaluation, semantic analysis, code generation. Those might be all different kinds of operations that aren't really closely related to each other, but they all happen to work on expression trees or on various kinds of composite structures. The second time when you might apply this pattern is when class relationships in the structure rarely change. In other words, we have leaf nodes and add nodes and subtract nodes and so on. But the operations change. We have printing, evaluation, semantic analysis, code generation, and so on. And we also have situations where the algorithms may want to keep state as they're traversing through the structure. So here's a picture that illustrates how all the pieces fit together. So as you can see here, we have two hierarchies. We have the visitor hierarchy and we have the element hierarchy. The visitor hierarchy is where you actually define the operations you want to perform. So in this particular case, we might have our expression tree visitor, which would be a base class, and then we would have various subclasses of expression tree visitor, printing the tree, evaluating the yield of the tree, and so on. That's one set of hierarchies. And you'll notice that this has a number of different visit methods, which are overloaded by the different types of elements or concrete elements that we define in our parallel hierarchy, the element hierarchy, that corresponds to the structure that we're dealing with. In our particular case, this structure is the composite for our expression tree and its nodes. So at the root of this, we have the component node, which is the element in the pattern. And then we have various concrete elements defined that inherit from component node. Things like composite add node, the various other types of nodes, composite binary node, composite unary node, and so on and so forth. And so what you see here is that as you subclass the visitor, you fill in all the various methods that know how to visit the various kinds of composite nodes that form the elements in the object structure. Let's take a look at how we might implement this in C++, and we'll look at a couple of different examples. First, let's take a look at the print visitor. That's the easy one. As you can see here, print visitor inherits from the expression tree visitor base class, and it fills in a set of hook methods, the visit methods, for every type of node in that composite that's rooted at component node. And then we can combine this with all kinds of different traversal algorithms. So we can print the tree in post order, we can print the tree in pre-order, we can print the tree in order, and so on and so forth. And by doing things the way we are, the code that we write is virtually the same. It uses the STL algorithms, we could use the range-based for loop, and so on. And it iterates over this. And for every node it gets back, every expression tree node it gets back from the iterator, it turns around and calls the accept method, passing in the print visitor, which will then turn around and print the elements by calling the visit hook method. Here's a sequence diagram that illustrates how this works. The iterator controls the order in which accept is called. In our case, it all depends on the traversal order of the tree. And as accept visits each of the nodes, they then perform the desired action to print that node. So the iterator starts out by saying, please accept this print visitor on the leaf node, for example, and that turns around and calls to the print visitor, and the print visitor turns around and prints the value at that leaf node. The next thing that would happen is we might get back a composite negate node from our iterator. We say, please accept the print visitor to that node. That node turns around and says, OK, visit me, and then that has the print visitor turn around and print out the particular type of node, in this case the minus sign, and so on and so forth. So you can see these relationships taking place between the iterator, the different nodes that it's iterating over, and the visitor. And there are subtle callbacks and interactions via something called double dispatching, which we'll discuss momentarily. Here's an example of how we might implement the evaluator visitor for this particular expression tree processing application. This example is a little bit more complicated because what we're doing here is we're not just printing out the values, we actually want to evaluate the yield of the tree. Once again, we inherit from a base class. We fill in all the various methods. And we also define a stack using C++ stack container adapter. And this is going to be a stack of int, because we're keeping our expression trees simple for the moment. And what it'll do is the implementations of the various visit methods will go ahead and push or pop the various operands on and off the stack. And when it gets to a certain point in the traversal, it'll go ahead and apply the corresponding operator, perform the result, and then push that back onto the stack. And this particular approach we're showing here works nicely with post-order traversals, where you can use a runtime stack to keep track of the ever-growing yield and results of the tree traversal. Here's an illustration that shows how this might work as a sequence diagram. Once again, the iterator controls the order in which these things happen by calling except. The except method then visits the appropriate node it's given, passing in the evaluator visitor to do the right work to evaluate the tree. So in this case, we call except on a leaf node. That turns around and calls the eval visitor and says, please come and visit me. The eval visitor says, aha, thank you. I will go ahead and grab your value, and I will push this value onto the runtime stack. Next, when we go and visit the negate node, that will turn around and say, when the accept method is called, it'll say, come visit me, please. The eval visitor, when it visits the negate node, will turn around and pop the item off the stack, negate it, and then push it back onto the stack again. And these things take place over and over again until we've gotten done traversing the entire expression, and the result will be held in the top node of the stack. So to go ahead and summarize the consequences of visitor, there's various pros we get from this. We have much greater flexibility. We can change the algorithms and the operations without affecting the object structure. As you can see, there's just a method called except that takes a visitor, and everything from that point can be driven by dispatching and either dynamic or static polymorphism. We separate concerns. You can localize the functionality in the subclass of the visitor without affecting the structure of the composite or the elements that you're iterating over. There are some downsides, however. Probably the biggest downside is it's a hard pattern to explain and understand, but there's also some other issues. There's rather tight coupling between visitor and element interfaces. So if you end up making new types of elements, you're going to have to go back and open up the visitor base class and add the appropriate visitor methods, which can start to have quite a bit of ripple effect through your overall design. From an implementation consideration point of view, this double dispatching is something that's supported natively in some object-oriented languages. In other languages like C++ and Java that don't support double dispatching as a language feature, then you have to do it via the pattern, where you pass various nodes to each other, pass various references and pointers, and do this double dispatch dance we've shown. You also have to keep in mind how generalizable do you want to make your object structure. The more specific, the easier the pattern is to work with static polymorphism, but you also have lots and lots and lots of methods defined on the visitor and its subclasses. The more generic, you can keep those interfaces a little bit narrower, but then you may have to do some dynamic dispatching as opposed to relying on overloading of operators and methods in order to do the static polymorphic dispatching. There's a number of places this pattern's been used. It's been used in some of the Smalltalk 80 compilers. It's been used in some rendering engines. We have actually used it quite a bit in the middleware that we develop for some of the generators that we have for transforming interface definition language descriptions into C++ or Java or other languages, or C++11 or STL versus more traditional mappings and so on. And we like to use the visitor pattern with the iterator because it makes it easy to write different backends that can be retargeted for different languages or different optimization scenarios without changing the basic structure of our solution and our composites. What we're going to do in the last portion of this part is we're going to go ahead and discuss a particular way of enhancing or working around some of the quirks of the C++ STL iterator abstraction. In particular, we're going to be coming up with a way to ensure the proper semantics of post-increment or post-decrement operations for STL iterator objects. In our particular case, the ET object, or ET iterator object, which is the expression tree iterator. if you take a look at the way that iterators work in C++ or C, then what you see is that plus plus in a pre-decrement form has slightly different semantics from plus plus in a post-decrement form. And everything, by the way, I'm about to say also applies to minus minus, the decrement operations as well. So assuming that you have an iterator to an expression tree, if you say iterator plus plus or iter plus plus, that will return to you the old value of the iterator and then increment its value by 1. In contrast, if you do plus plus iter, which is called pre-increment, that will give you back the incremented version of the iterator. So that's the context for what we're discussing here. And what we want to be able to do is make sure we have the right semantics for this. So here are some of the constraints and forces with STL. It turns out that pre-increment and decrement iterator operations are very simple to implement. All you need to do is when they're called is they turn around and increment the iterator by 1 and then return a reference to the value that was incremented. Conversely, for post-increment and decrement iterator operations, what happens in that case is you have to first make a copy of what you already had, then increment the iterator, and then return the copy of the old version before you incremented it. So that's necessarily going to be a little bit more expensive, a little bit more complex to do. Since our ET iterator uses the bridge pattern, moreover, we have to think carefully about how the abstraction or interface portion of this pattern, which is operator plus plus, post-increment or post-decrement, is going to be able to find out the appropriate type of the hierarchy of nodes that is pointed to by the iterator impl. By the way, just as a quick side note, it's a good idea to get in the habit when writing STL code of saying plus plus iterator as opposed to iterator plus plus, because then these complexities we're talking about don't end up causing your program to be bigger or slower. The solution we're going to apply here is to clone a new instance of the appropriate iterator implementation using a prototype. And if you take a look at this diagram, it illustrates the basic structure of the solution. What we do is we have our ET iterator impl base class implement a pure virtual clone method, and all the classes that inherit from that class, in order, iterator impl, pre-order, iterator impl, post-order, level order, iterator impls, and so on, they all implement that particular clone method to make a deep copy of themselves. And the nice thing about doing this, as you can see in the slide here, and we'll look at this and expand it a bit more in just a couple slides, you can see that when the operator plus plus post-increment operator is called on the abstraction portion of the bridge interface, all it needs to do is it just needs to be able to say, hey, implementation, clone yourself without having to know or care anything about the details of which particular kind of subclass is actually being held by that interface portion of bridge. And then it'll go ahead and get that clone, stick it into an iterator, which in this case is an expression tree using our type def we showed earlier, and then it increments the iterator by 1 and returns a copy of the original one before it had been incremented. As always, we use the bridge pattern to encapsulate variability, to simplify memory management, and in this case, to be able to make things work seamlessly in the context of value-based STL algorithms and containers. So the way in which this actually works, if we kind of zoom down a little bit into the ET iterator impl class itself, we see that it has those operations for iterators like plus plus and operators dereference and so on. And then it also defines this clone hook. Now what's interesting here is that you can see that clone is a pure virtual method, which means it has to be overridden by subclasses. And clone returns a pointer to an ET iterator impl. It returns a pointer to what looks like itself, its base class. In fact, of course, the subclasses of this interface are going to override clone and provide deep copies of themselves, returning those things as pointers to ET iterator impls. From a commonality and variability point of view, the commonality part is we have a common interface for cloning things that return these base class pointers. And then from a variability point of view, we have a common way of being able to subclass the particular base class, the ET iterator impl, and then being able to define specific clone methods that know how to clone themselves because they know what their types are. The way in which this is done, the way in which we organize these various roles and responsibilities is driven by the prototype pattern, which is a Gang of Four pattern. That's an object creational pattern. And one reason it's object creational is because you don't have to know the specific details of the type of class that's being cloned. That can be hidden behind the abstract clone interface. The intent of this pattern is to specify the kinds of objects to create using a prototypical instance, and then create new objects by copying this prototype. As you saw in our example, our prototype here is the thing that points to the base class, but when you call clone, it's the subclass that knows how to make the right kind of object. You should consider applying this pattern under several circumstances: when the classes to instantiate are specified at runtime, when there's a need to avoid the creation of a factory hierarchy, and if it's more convenient to copy an existing instance than to create a new one. The structure that's shown for the pattern is illustrated at the bottom of this slide as a UML diagram. As you can see, you have the client, which in our case is the ET iterator, which is the interface part of the bridge pattern, and it's going to go ahead and call clone, and when it calls clone, it'll call clone on its prototype, which in our case is the ET iterator impl, which, as you can see, is actually playing a couple of different roles here. It's playing the implementer portion in the bridge pattern. It's also playing the prototype portion in the prototype pattern, illustrating so-called high pattern density. And then we can go ahead and subclass from prototype to make, from ET iterator impl, to make different kinds of concrete prototypes. Things like pre-order ET iterator impl, post-order, level order, in-order, ET iterator impls, and so on and so forth. Here's a quick illustration of this code in C++ to show how it's done. The Java code would be virtually the same. What we're going to do in this particular case is we're going to go ahead and show first the operator ++ post increment method defined on ET iterator, which is the bridge interface portion. And as you can see here, when it gets called, it turns around and it delegates down to whoever it's part of its implementer hierarchy, whoever it's pointing to there, and it says, hey implementation, clone yourself, please. And it takes that back as an ET iterator impl pointer, stores it with the ET iterator, and then it goes ahead and it increments the iterator by 1 and returns the original copy. And this uses the various characteristics of the bridge pattern to shield the various details of how things are working. There's no need for operator ++ for pre-increment to know the specific details of what impl actually points to. When clone is called, it'll turn around and call the clone method on whatever the actual type of that object is. Is it a pre-order? Is it a post-order? Is it level order? Is it in order? And so on. And that clone method, because it knows what it is, will turn around and make a copy of itself using its copy constructor. And it returns the instance to itself, a pointer to the instance of itself, as the return value from clone. And that comes back, in this particular case, as a pre-order iterator impl, but it's used as an ET iterator impl. So it's a common way of being able to do this. The consequences of applying this particular pattern is you can add and remove classes at runtime, cloning them as you need to. It reduces the amount of subclassing that's actually part of the client code, because that can be hidden behind the clone interface. And the lexical dependencies can be minimized. There are some downsides, of course. One issue is that if you're going to use this pattern, you have to create the prototype even if you don't ever create any other instances. So you're paying a little bit of overhead that may be unnecessary. And if you have circular references between the classes, then this pattern doesn't really apply. There's a number of implementation considerations to keep in mind. You might want to sort of centralize your various prototype in a prototype manager, maybe make that a singleton perhaps. There's the issue of what kind of copies do you make? Do you make a deep copy? Do you make a shallow copy? There's trade-offs. You may need to do more reference counting in some cases, which could make your code more complicated. And then there's also the issue about whether or not you can easily initialize the clones of the subclasses in a uniform interface, or is that too constraining and too restrictive? There's a number of known uses of this pattern. One of the first most widely known use was in the ThingLab, which is an object-oriented language that was used in ThingLab. Jim Copleen's book, Advanced C++ Styles and Idioms, has a number of examples of prototype being used. And there are other examples of debuggers and drawing editors and so on that also make use of this pattern. So to wrap up this section, the iterator and visitor patterns are used to traverse expression trees and perform various designated operations to print them or evaluate them or optimize them and so on. And we used the prototype pattern in order to be able to simplify portions of our iterator so it would work seamlessly in the context of C++ and STL value-based copy semantics. Another nice thing about applying these patterns is it was able to completely decouple the traversal and actions performed on a structure on the expression tree from its structure, and we could go ahead and add new operations without affecting that structure, without breaking the existing commitments we've made to clients that relied on those interfaces to begin with.